Okay, we want to take a look at what it means for the limit as x approaches c of f of x to equal L. Certainly we've analyzed a lot of these limits. Okay, well, in order to attempt to evaluate this, or to use our definition we're about to use, we have some requirements for f. F has to be continuous. Notice it doesn't have to be differentiable, just continuous, on some open interval containing c. Now it doesn't have to be continuous at c itself. So in red up here, I've got f is continuous, right up in here. F is continuous on an open interval containing c, except maybe not at c itself. So it might have, like I've drawn here, an open circle. Well, we say the limit exists if, and the limit's going to be L. Notice I've got in my graph here a function in red, that's f, and I've got L, which is the y value where the open circle on f occurs. Now that circle might be open, might be filled in, it doesn't matter. Okay, now the way this definition works is I'm going to draw, and have drawn, these black, right here, now yellow, bars. They're at the same distance above and below the limit. That distance is always denoted by a Greek letter called epsilon. So the yellow bar is L plus epsilon. The other yellow bar below is L minus epsilon. The way the definition works is, if I can always find about C, a circle, and down here I've got a circle around C in purple, and the radius of that circle is always called Greek letter delta. So down here I've got this circle, which is going to turn into a different color now. Using my highlighter, it's now going to be a green circle. As long as I can find a circle about C, delta units to the right and delta units to the left, that's lowercase delta here, okay, such that every function value, when I send it up, will lie between, and we'll highlight this in yellow and green this time, the entire set of values that are in this circle down on the x-axis, when we apply the function to them, they have to lie between the yellow lines. If I can find that circle of values about C, no matter how tightly together we squeeze the yellow lines around L, then we say the limit exists. So here it is formally. If, for all epsilon greater than 0, that's some positive distance away from the limit, there exists a delta greater than 0. That's some positive radius on this circle around C, such that 0 less than x minus c less than delta. So what's that say? That's saying that every x value is in my green circle. If, when I apply the function to every x value in the green circle, all of my f of x's are between the two yellow lines. And how would you say that formally? That's f of x minus L. The distance from f of x to L is less than epsilon, which means it's between plus epsilon and minus epsilon. Then the limit exists, and then the limit as x approaches c of f of x equals L. Now, what might IU want you to do with a definition like that, other than cry? Well, here might be one. So we know that the limit as x approaches 2 of x cubed equals 8. Suppose the question said, for an epsilon value of 1, suppose we want to keep our y values between 1, find a delta value, a radius around 2, that works. So I've got a couple examples here. First thing I just guessed, maybe 0.1 would be close enough for delta. In other words, if I want to be within an epsilon 1 of 8 for the function values, that means all my function values have to be between 8 plus 1 and 8 minus 1. In other words, between 7 and 9. So the first thing I tried here, I tried a delta value of 0.1. In other words, if I get within 0.1 units of 2, that would be between 1.9 and 2.1, will my y values be close enough? In other words, will they be between 7 and 9? And the answer is no, they won't. 1.9 cubed is 6.9, that's under 7, and 2.1 cubed is 9.2. So that value for delta doesn't work. So in red there, I tried a delta value of 0.01. When I cube 1.99, I get 7.88. Well, that's between 7 and 9. When I cube 2.01, I get 8.12. So I've found, for an epsilon of 0.1, I have found a delta such that all the values that are within 0.01 rather, of 2, the y values will be within 1 unit of 8. Now, how do I know, in this particular case, how do I know that because these two values here were in the right range, how do I know everything in between them? Well, I know it in this case because my function x cubed is an increasing function. So if my n's were within that value, the 1.99 and my 2.01, then everything in between them would have to have been. That little argument doesn't always work for functions that fluctuate up and down in a range, however. But there's one example. Now, another way that they might want you to do this is to do a delta epsilon proof. Okay. Well, that scares people because it sounds like proofs in geometry, and it is a little bit back like that. Well, the proofs that they would ask you to do are going to be pretty simple, even simpler than the x cubed, because that's even difficult as delta epsilon. So they might have you do this. Prove that the limit as x approaches 2 of 3x plus 1, well, we could see that has to be 7, right? Okay, well, the trick to this proof is really to work it backwards. So you start off by assuming what you want to prove. Assume that the absolute value of 3x minus 7, minus 1, minus 7 is less than some epsilon. Now, why have I written that? Because the second half of our rule, of our definition of the limit, has the absolute value of f of x, and that was my f of x up here, minus what we're saying is the limit, L, and that's my 7, is supposed to end up being less than epsilon. What I want to do is work this backwards now until I can get x minus 2 in absolute values. Now, here's how it works. I can take and simplify the 3x minus 1 minus 7 to be the absolute value of 3x minus 6, less than epsilon. Okay, I can write that as the absolute value of 3 times the quantity x minus 2 is less than epsilon. A property of absolute values is that I can write this as the product of the two absolute values, in other words, 3 and x minus 2, and since absolute value of 3 is just 3, this now can be written as 3 times the absolute value of x minus 2 is less than epsilon. And finally, I can divide both sides by 3. This gives us that the absolute value of x minus 2 is less than epsilon over 3. Well, this epsilon over 3 is exactly what our delta should be. So we're going to choose delta to equal epsilon divided by 3. And since every step of this proof reverses, I have to go to a new page, we will write since all steps reverse. Which means you can reverse factoring by distributing, you can reverse multiplying by dividing, or adding by subtracting. Since all steps reverse, 0 less than the absolute value of 3x x minus 2 less than our delta, which is that epsilon over 3. You could write that either as delta or epsilon over 3. That if that's true, then the absolute value of our function, and I'm going to write this on the next line because I'm running out of room, then absolute value of our function, which was 3x plus 1, minus our limit, has to be less than epsilon. And because this statement has to be true, because all steps reversed, then we've proven, or what we were trying to prove, therefore, the limit as x approaches 2 of 3x plus 1 equals 7. And if it's going to be fancy, you can write QED, thus it is proved. Okay, what I would like you to do is one problem. Homework. I want you to prove that the limit as x approaches 3 of 2x minus 1 equals 5 using a delta epsilon proof. And turn that in for me.